coal gasification, and coal-to-liquids projects in China and India. Coal renaissance in Asia. Energy security and economic challenges. The resurgence of coal gasification and coal-to-liquids (CTL) technologies in Asia reflects growing concerns about energy security, geopolitical instability, and industrial self-reliance. Both China and India have recently accelerated investments in coal-based chemical and fuel production infrastructure to reduce dependence on imported oil, liquefied natural gas, LNG, and petrochemical feedstocks. These initiatives gained renewed strategic importance following tensions in the Middle East and disruptions surrounding the Strait of Hormuz, a critical maritime route for Asian energy imports. Although many of the projects were planned before the regional conflict, the crisis reinforced long-standing national policies emphasizing supply chain resilience and domestic resource utilization. Coal gasification involves the partial oxidation of coal at high temperature and pressure to produce synthesis gas, Syngas, primarily composed of carbon monoxide, CO, and hydrogen, H2. Syngas serves as an intermediate feedstock for manufacturing methanol, ammonia, synthetic natural gas, olefins, fertilizers, and liquid transportation fuels. Modern coal conversion technologies, therefore, integrate the energy, petrochemical, and materials sectors into a single industrial platform. Expansion of coal chemical projects in China. China has developed the world's largest coal chemical industry over the last 2 decades. Since commissioning its first commercial coal-to-olefins facility in 2010, the country has invested hundreds of billions of dollars in coal-based petrochemical complexes. These facilities convert domestic coal reserves into higher-value chemicals such as methanol, ethylene glycol, olefins, vinyl acetate, and synthetic fuels. A recent example is the multi-billion-dollar coal-to-ethylene glycol project initiated by Hengyi Petrochemical in Xinjiang, Western China. The project reportedly represents an investment of approximately $3.8 billion and is designed to produce around 2.4 million metric tons of ethylene glycol annually. Ethylene glycol is a major precursor for polyester fibers and polyethylene terephthalate, PET, plastics. The complex is also expected to manufacture dimethyl carbonate, a compound increasingly used in lithium-ion battery electrolytes and green solvents. The rationale behind such investments extends beyond economics. Chinese industrial policy increasingly emphasizes autonomous controllability of strategic supply chains, particularly for energy-intensive industries vulnerable to fluctuations in crude oil prices and geopolitical disruptions. Coal remains abundant within China, accounting for nearly 60% of the nation's primary energy consumption, according to the International Energy Agency. By converting coal into petrochemical feedstocks, China can partially substitute imported hydrocarbons while stabilizing domestic industrial production. In addition to energy security, coal chemical projects are often integrated into regional economic development programs in resource-rich provinces such as Xinjiang, Inner Mongolia, and Shanxi. These regions possess extensive coal reserves, but comparatively limited industrial diversification. Consequently, coal conversion projects are promoted as mechanisms for employment generation, infrastructure expansion, and value-added utilization of domestic mineral resources. However, China's coal chemical sector also faces increasing scrutiny because of its carbon intensity. Coal gasification and CTL technologies generate substantially larger greenhouse gas emissions than conventional oil or natural gas-based petrochemical pathways. To address these concerns, Chinese authorities are encouraging integration of renewable hydrogen, carbon capture and storage, CCS, and energy efficiency improvements into next-generation coal chemical facilities. Researchers and policy analysts suggest that green hydrogen may gradually displace coal-derived hydrogen in the future, potentially reducing the long-term role of coal-based chemical production. India's coal gasification strategy. India has similarly intensified efforts to develop a domestic coal gasification industry. The Indian government recently approved a large-scale initiative valued at approximately $3.9 billion aimed at supporting coal gasification projects across the country. The program targets the conversion of roughly 75 million metric tons of coal annually into products such as methanol, ammonia, synthetic natural gas, and fertilizers. India possesses substantial coal resources, with estimates exceeding 400 billion metric tons of coal and nearly 50 billion metric tons of lignite reserves. Coal currently contributes close to half of the country's primary energy supply. Despite this abundance, India remains heavily dependent on imported LNG, crude oil, methanol, ammonia, urea, and metallurgical coke. Rising import expenditures and exposure to volatile international energy markets have motivated policymakers to pursue domestic alternatives. The government views coal gasification as a strategic approach to reducing vulnerability to geopolitical disruptions in West Asia. Imported petrochemical intermediates and fertilizers impose a significant financial burden on the Indian economy, and domestic coal conversion is expected to partially offset these imports. Officials also project substantial employment generation through new industrial clusters associated with gasification and downstream chemical manufacturing. Several Indian public sector enterprises, including Coal India Limited and Bharat Heavy Electricals Limited, have participated in pilot projects involving underground coal gasification, methanol synthesis, and ammonia production. India is additionally exploring coal-to-hydrogen and coal-to-synthetic natural gas technologies to diversify industrial feedstocks and transportation fuels. Nevertheless, economic and environmental challenges remain significant. Indian coal often contains high ash content, complicating gasification efficiency and increasing waste generation. Water consumption is another critical issue because coal gasification plants require substantial quantities of cooling and process water, particularly problematic in water-stressed regions. Fischer Tropsch coal-to-liquids technology. An important extension of coal gasification is the coal-to-liquids (CTL) process, particularly via Fischer Tropsch (EFT) synthesis. Developed in the 1920s by German chemists Franz Fischer and Hans Tropsch, the FT process converts syngas into liquid hydrocarbons, including diesel, gasoline, waxes, and jet fuel. The process generally consists of three major stages: coal gasification to produce syngas, Syngas conditioning to adjust the H2 to CO ratio and remove impurities such as sulfur and particulates. Catalytic Fischer-Tropsch synthesis, using iron or cobalt-based catalysts to generate long-chain hydrocarbons. Depending on catalyst composition and reaction conditions, the FT process can selectively produce synthetic diesel, aviation fuels, lubricants, or olefinic feedstocks. Iron catalysts are commonly used for coal-derived syngas because they tolerate higher carbon monoxide concentrations and facilitate the water-gas shift reaction. Historically, CTL technology gained prominence in countries facing oil supply constraints. Germany relied on synthetic fuels during World War II, while South Africa expanded CTL production during the apartheid era through Sasol to overcome international oil embargoes. Sasol remains one of the most successful commercial examples of large-scale FT fuel production. China has also invested heavily in CTL facilities. Companies such as Shenhua Group developed direct and indirect coal liquefaction plants in Inner Mongolia and Ningxia. Some facilities produce synthetic diesel and aviation fuel at a commercial scale, though expansion has slowed because of environmental and economic concerns. Economic viability of coal-to-liquids technologies. The economic feasibility of CTL and coal gasification projects depends heavily on oil prices, carbon policies, capital expenditure, and local resource availability. CTL facilities require extremely high upfront investments due to the complexity of gasifiers, oxygen plants, FT reactors, hydrogen generation units, and emission control systems. Commercial-scale CTL plants often cost several $billion and require long construction timelines. Profitability generally improves when crude oil prices remain high for sustained periods, making synthetic fuels more competitive against petroleum-derived products. Conversely, low oil prices can rapidly undermine CTL economics. Coal availability is another important factor. Countries such as China and India possess extensive domestic coal reserves, reducing feedstock costs and enhancing strategic energy independence. For energy-importing nations, converting coal into chemicals and fuels can reduce exposure to international supply disruptions and maritime choke points, such as the Strait of Hormuz. However, CTL fuels are associated with significantly higher life-cycle carbon emissions than conventional petroleum fuels unless combined with CCS technologies. Coal gasification also produces substantial carbon dioxide during syngas generation and water-gas shift reactions. Consequently, carbon pricing mechanisms and climate regulations may substantially reduce long-term economic competitiveness. Water demand further complicates project viability. CTL facilities consume large amounts of water for steam generation, cooling, and gas purification. This requirement limits deployment in arid regions unless advanced water recycling technologies are implemented. Despite these challenges, governments continue to support coal conversion technologies because they offer strategic advantages beyond direct profitability. These include employment generation, domestic industrial development, reduced import dependency, and enhanced resilience during geopolitical crises. Environmental and strategic outlook. The future of coal gasification and CTL technologies will likely depend on the balance between energy security and decarbonization goals. China and India both seek to secure domestic energy supplies while simultaneously committing to emissions reductions and renewable energy expansion. Emerging approaches involving biomass co-gasification, renewable hydrogen integration, CCS, and low-carbon synthetic fuels may partially reduce the environmental footprint of coal conversion technologies. Hybrid systems combining coal, biomass, and green hydrogen could enable gradual transition pathways for existing industrial infrastructure. Nevertheless, critics argue that large-scale investment in coal-based chemicals risks locking economies into carbon-intensive pathways for decades. Environmental analysts emphasize that each new coal conversion facility creates long operational lifetimes and potentially delays adoption of cleaner alternatives such as renewable hydrogen, electrification, and bio-based chemical manufacturing. Even so, for rapidly industrializing economies with abundant coal reserves and growing energy demands, coal gasification remains an attractive strategic option. The current expansion of coal chemical infrastructure in China and India demonstrates how geopolitical uncertainty, resource nationalism, and industrial policy continue to shape the global energy landscape despite accelerating climate concerns.